And I have to say, this is probably one of the most beautiful places that I've come for a Perl event. It's just beautiful here. I have the great fortune of having a room on the back of this hotel, so I can just lie on the bed and look at the beautiful mountains. It's wonderful. I have the sort of privilege of having come from a quite pretty place as well. Some of you may know that I live in the Czech Republic, and you might at this point then be saying, "Oh, so is that the astronomical clock in Prague?" And no, it's not. This is actually the astronomical clock in the city of Olomouc. Who's heard of Olomouc? Okay, so popular city. Do you know what Olomouc is famous for in the Czech Republic?
Astronomical clock?
No. It's famous for having really smelly cheese. Now, just to top this off, a local dish is garlic soup containing this smelly cheese, which is the perfect introvert dish because nobody will come anywhere near you. That's the day. It's just great. Now, back to the clock. I don't actually know a lot about this clock. I do know that the reason that the figures look so, like, wholesome workery is because the original was damaged during the Second World War, and then when they came to rebuild it, it was the communist times, and they said, okay, let's put some good, wholesome worker figures on this clock. But the faces, like, I don't have a clue about this. I don't know much about how they work or what they are, the mechanism behind them, and I think that kind of is the way that people maybe feel a bit when they listen to all of the interesting words around the Perl 6 optimization efforts. We throw around words like deoptimization, which sounds like a terrible idea. Why would we deoptimize something? Doesn't that mean we make it go slower? Why would they spend so much effort and pain on deoptimizing? And there's a whole bunch of things like that. So what I want to do in this session is just take a little bit of a look at why making Perl 6 faster is a fairly challenging problem. And also show you some of the techniques we're taking at a fairly low level, down at the virtual machine level, to attack this problem, and share with you a bit of the interesting computer science that we're throwing at this problem. So first of all, let's just look at the challenge. So way back before I was doing Perl 6 things, someone had this great idea. Let's write Perl 6 in Perl 6. Now, I have to say there's a lot of good things about this approach. One of them, of course, being the community aspect, that it's very easy for people to come and start contributing because it's already in the language that they're using. And it's also very nice that if you don't know how exactly something works, you can often go and have a look. But the challenge of this is, let's take a language that's ambitious, that's got lots of powerful abstractions and late binding, and implement this challenging thing in a language that we haven't implemented yet, let alone figured out how to make fast. Just to give you some examples, you might look at indexing an array, and if you look at a lot of typical dynamic language virtual machines or runtimes, when you index an array, that goes down to something low level, written in C pretty fast normally. But in Perl 6, oh no. That is a call to a multiple dispatch subroutine, which has the wonderful name post circumfix. So we know what a postfix is. Okay, a postfix is a thing that goes after a term, like the plus post increment. A circumfix, well, that's a thing that goes around a thing. So a post circumfix is, of course, a thing that's around something but after a something. Okay, so there we go. And this is the post circumfix implementing array indexing. Now this has a bunch of overloads, one for a single index, one for taking a whole list when we want to slice, one that takes a bit of code, that star -1 is a little closure that takes the number of elements when we invoke it and subtracts 1, and that's how you get at the end of the array. So now we have called this, and you might kind of say, okay, that's kind of nice, because that means that we can overload array access. But it's a bit of a pain, because for your new array type, you'd have to implement all of these. So actually what it does is for each element it wants to access, it makes a call to the addPos method. Okay? And the addPos method takes a single index. This is normally what you implement if you want to make your own custom array-like type. And then that's where the magic actually happens. We get the element, we return it if it's already there. If it's not already there, we actually have to make up a scalar and stick something on it so that if you assign to it, then we auto-vivify the slot in the array. And at this point, you might be starting to understand that there's quite a lot of work going on here. Okay, an array index is a multiple dispatch followed by a multi-method dispatch, because that's done with multi-methods too, followed by the actual work. Looping over the lines in a file. Oh my goodness. Okay, so we get an iterator. Okay, so we call the lines method. It gives us back an iterator, and that's fine. That's a one-off. And then to get something from the iterator, we call pull1. Okay, which means I want to pull one element from this iterator. So that's a method call. Pull1 then goes to a decoder object, because of course we support pluggable user space encodings, so you can plug in your own encodings if you want. But that's a method call on the decoder to consume line chars. Now consume line chars might actually fail because it's run out of stuff in the buffer, and then we, if it fails occasionally, should go to some slow path and get some bytes off the disk or wherever and fill it up again. And then we have finally the line that we wanted to read, and at that point then we need to invoke the loop. And if you've seen loops in Perl 6, you'll know that for loops basically are a case of map, so it really is a closure that we're invoking there. And we pass the line as an argument to it, and finally we can process the line. Whew. Okay, all these darn calls. It's a good job that calls can be so cheap in Perl 6. Oh wait. Method resolution. Yeah, we have a meta object protocol, so you can change what method lookup does. But at least types, you know, and checking we got the right type should be, oh wait, it's not. That's pluggable too. Well, at least maybe we can find a really cheap way to represent the call stack and, you know, each of the call frames have entered. That would have been nice, except we have continuation powerful constructs in Perl 6, so no. Stack frames are first class. So if you've seen any of those fancy pseudo packages like outer and caller and so on, which let you go and introspect the symbols in the outer and caller scopes, okay, so that means we actually have to have these as first class, because you can actually take the outer symbol and pass it somewhere or store it somewhere and then talk about the outer variables of a scope you were in, like, you know, 1,000 instructions ago, way down the line. Also, just as if this wasn't enough, you might say, but we can try and be clever and look at type checks that we do and try and eliminate duplicate ones. Or we can maybe, you know, take things out of a scalar once and cache that. And the answer is, well, not quite, because actually a mix-in can change the type of an object at a distance. And then there's a few extra things, like, you know, every frame has an exit handler, so whenever we leave it, we have to check if we should run that. Okay. So hopefully now I've convinced you that we set ourselves up for a little bit of a challenge in this. So let's talk just a little bit about the Rakudo compiler architecture and then dig into how we're addressing some of these problems. So we take Perl 6 source code, we compile it into bytecode that runs on some virtual machine. I'll be talking about MoarVM today. In between here we have the Perl 6 compiler. It's written in NQP, which is a subset of Perl 6. And basically it uses a grammar to pass it. It has a callback to what we call an actions class. So each time we match a rule in the grammar, we make a call. That call makes up a tree, and gradually we work our way up. We stitch this all into a single big tree, which we call an abstract syntax tree. Why? Because it's abstracted away from the syntax. So in Perl 6 there's various places where, you know, there's more than one way to write a very similar thing, and then we sort of try and reduce it a little bit. So that is then thrown into a code generator, and that's how we get the bytecode. So the compiler itself is a Perl 6 program. It's running on the same virtual machine instance as the program that it compiles. So sometimes when people hear that we compile stuff into bytecode, they say, oh, so I can't do like one-liners and one-off scripts anymore. And the answer is, yeah, sure you can. we just have the bytecode in memory, okay, and then we run it, so it never hits disk. For modules, we actually do cache the bytecode on disk, which sounds like a somewhat easy thing to do and turns out to be an absolute horror. And of all the things I'm really happy somebody has taken off my plate in Perl 6, this is number one, because it is a real, yeah, thank you. So eval just calls into the compiler, runs it. This has the interesting consequence, we have to be able to garbage collect bytecode. But fine, we can do that. So what about sticking optimization in here? Well, this wasn't quite the whole truth. Actually, that's the real truth, or a bit truthier. As truthy as I need to do for this talk. So we have an AST optimizer in there. And it takes in this abstract syntax tree, it knows some stuff about Perl 6 semantics, and it spits out a better version of that tree. We do a few things in there. We do things like constant folding. So if you write somewhere in your program, 1 plus 1, we'll actually turn it into 2. Okay, and you might say, when would I ever do that? And the answer is, well, you probably wouldn't, except maybe you might have a constant declared somewhere. And because constants are done at compile time, then we can fold them. We also try and take some lexical variables, and lexical variables are things that you can see from an inner scope. But they also have some overhead as a result of that. They're a bit harder to reason about. So we turn them when we can into locals. We're not very aggressive at that yet. We'll get more so in the future. We also try and take some nested scopes, because every scope in Perl 6 is conceptually a closure, but we then try and flatten them down to try and save a lot of the closure cloning operations. We do some things where you have a native operator, say a plus, operating on a native integer and another native integer, and we just turn that into a simple add instruction rather than a subroutine call. And we do a few other assorted little rewrites that try and cheapen things up. So for example, if you write a simple expression using a junction, for example, if A is equal to 1 or 2, we'll actually go and turn that into reading A once and then checking if it's equal to 1 and checking if it's equal to 2. So it's as cheap or cheaper as if you'd actually written it out longhand. Now, all of those are fairly localized, except this inlining here, I guess, is not. You might think, well, shouldn't we do a lot more there? You might have heard of this saying before, okay? Don't put off until runtime that which you could do at compile time. Okay, you might have heard that, and that would suggest we should go optimizing really hard. The thing is, if you're writing scripts, or you're writing a module and doing little changes and running the tests, for the language user, there isn't actually a compile time and runtime, there's just time. Okay, so if we spend a lot of time trying to do clever things in this AST optimizer here, then we're actually delaying the getting the real work done. And if we actually have a bunch of tests, then we're just running a test suite. There's not a lot of repeated work in that. The same code doesn't run many times. It's not going to make very much difference at all. So the other thing is, though, and it gets worse. Now, suppose that we did take a module and say, well, it's a module. Let's invest a lot of analysis and time on this. Very often we're missing the context. We don't know exactly how it's going to be used in the program. We don't know what sort of things it's going to be passed. And the usage patterns might vary enormously between different programs. So one of the interesting things to consider is, how many compile times are we allowed? And the answer is, well, we can have as many as we want. In fact, the idea of just-in-time compilation is that we do some simple level of compilation at first, and then later on, we do another round, maybe down in the virtual machine, perhaps off to machine code or something like that, and we get another chance to do a bunch of optimization. So I've kind of rewritten this saying as only doing this compile time, something that couldn't be done better or more simply in a later compile time. And that's pretty much the attitude that we adopt to what goes into that AST optimizer. So that is why we don't do a load of clever stuff at that point. So that's talk a bit about some of the problems we face when we want to optimize Perl 6 code. I think that there's a lot of what I call known unknowns. What do I mean by that? Well, let's just take a really simple module. So this is just a subroutine that gets the average number of characters on a line. So a simple problem. We pass it a handle, okay, it loops over the lines, it adds up the number of characters on the line, it adds up the number of lines, it does a division, and we really hope the file wasn't empty or we're in a big bother. And what don't we know about in this? Well, we don't know if it's going to actually run because they didn't guard against the division by 0. But worse than that, we don't know anything about the types of these parameters. Okay, we might guess that that could be an I/O handle, though there's no real way the compiler could know. We might, as a human, be able to guess that if we're reading a line from a file, it's probably going to be a string, but we can't, in general, reason about this very well. So we don't know the types of those. When we have a method call, you might say, well, it'd be nice if we could figure out what we're calling and not have to look up the method by name every time. But actually, we don't know the types of the method invocants either. We don't know what we're calling lines on, we don't know what we're calling chars on here. You'll see even a simple operation like getting the number of characters on a string, we don't really know. We don't know the types of arguments to operators. So this division here, or more importantly, this addition and assignment, we don't know what the types of the two arguments is. You might say, well, that starts out as an int, so we know. But suppose that line.chars, we don't know what line is, we don't know what line.chars method is, we don't know what it returns, okay? So we have to assume it could be anything. So we don't actually know the type of total chars is going to be consistent. Again, we're a little bit stuck because every method is a multiple dispatch. So we'd like to try and do something with that, but we don't have a clue. And you might say, well, in Perl 6 you can put type annotations on things. So we could take this code and we could write, stir here, int here, IO handle here. But what if there was mixins? Okay, or what if there was subclasses and subtyping? Just because you have a type annotation doesn't actually mean that you know exactly what you have. Even if we put string on there, we actually have to spend the time checking that this method really did give us back a string. If we put IO handle there, we have to check that's what we get. So, and then it goes further. We do a lot of higher order programming in Perl 6. What if I get past a closure? Something to call back. In a given use of a module, it might turn out that particularly if we just sort of, we have a logging callback and we set it, it'll be the same call every single time. But of course we can't, in general, know that, so we can't try and do smart things. And then, even more fundamentally than not knowing much about the problem and the types, we don't even know if the investment would be worth it. What if this only runs on a file that contains 10 lines, and that's the program over? Okay. Now, sure, all of this slow path code is going to chug, but not that much. Okay, 10 lines is really not a lot. The investment that we would put in to trying to make this fast and do a lot of clever analysis would never actually be paid back. We don't know if it's worthwhile. And if you think about loading a load of modules, we would actually have no idea what bit of those modules you were going to use and what we should spend time on. So basically, this is a situation. We don't know what to spend time optimizing, and even if we did, we don't know actually what to optimize it for. Okay, which seems like a pretty bad situation to be in. Now, dynamic problem. Okay. Well, a lot of people look at this and they say, dynamic problem. Dynamic is the problem. So then what you say is, it's kind of like, well, let's try and build a dialect of Perl that has a bunch of restrictions. Which you could do. But I say dynamic problem, dynamic solution. Okay, so if you can't beat them, join them. So instead of trying to actually reason about the program statically, let's try and understand the program as it runs dynamically. So let's take our interpreter, which runs this bytecode, and let's make it just make little notes about what it sees. So each time we call a subroutine, or a method, or a block, we'll say, oh, we called this. Whenever we see some interesting type, we'll say, oh, we saw something of that type. It was a string, or it was an int, or it was a scalar, or something like that. Can actually that be done fast enough? And the answer is, well, yeah, we can do it pretty unobtrusively. Needs a bit of engineering, but you can get it down, we have in MoarVM anyway, to about 24 bytes per entry on a 64-bit platform. Actually, I can show you the data structure we have there. So these are the events that can happen, okay? So we have the entry to a call frame. We can have a parameter. Now in Perl 6, a lot of parameters receive a scalar, okay? And the scalar contains an int. And we're interested in both. So we actually log the parameter decontainerized type. Decont means taking something out of a scalar, okay? Now, we also have types that we're interested in. So when we look at lexicals or attributes, it's a bit hard maybe to reason about what they will be, but we can see what type they normally have. We can also log things that we've been told will always resolve to the same symbol. The compiler can do some analysis and figure that out. We also have a place where we log invokes. So what we say is, okay, at this location we call chars, and actually the method we go to is reliably the chars method on the string object. Okay, there's not an overload here. Also return types we track, so we know what we're getting back. And OSR points I'll come back to a little bit later. But effectively they are points at the end of a loop, and it counts up how hot a loop is. And I'll show you why we want that in a bit. So then we have the little entry struct here, and all it is a kind, which is the enum you saw up above. You might say, why didn't you make it an int 16 so that we can compress this, or an int 8? And the answer is it's not worth it, because the compiler will sneak in alignment stuff in C anyway, so it doesn't matter. Here we keep what I call a correlation ID. So whenever we call a subroutine and we're in the unoptimized code, we just give it the number. Okay, give that call the number. So this is call number 42. And then all of the events that are inside of that subroutine, we just scribble a 42 on. And the reason for this is that what we want to do later is try and reconstruct the stack and understand what called what, and what returned what type to what, and all of these things. But we don't have time to try and build all of that fancy model, because we're trying to run the user's code as well. So we just do the cheapest thing we can, which is just throw an integer in there, and something can put it back together later. And then we just have all of these different sections. Okay, it's a union, so they all overlap in memory, and that's how we get it nice and compact down to the number of 24 bytes. And here you can see that, for example, for type, we say what sort of type it was. Okay, we have some flags like was it concrete or not, and we also keep the bytecode offset. And that is what lets us later map. This is, again, it's very cheap, okay? We just log a program counter, and later we can correlate that with an actual instruction in the program to understand what sort of instruction resulted in this type. So what we're doing is just throwing information into a buffer as quickly as we can, trying to spend as few cycles as we can on it, saying what we saw. And those, when the buffer is full, are thrown into a concurrent queue. And there's a thread waiting to receive them. Okay, and that thread then simulates the call stack and replays all of these events on it. And what it gradually does is builds up a statistics model about what sort of things we saw. So let's just take this example program. Okay, we open a big file. We are going to count up the number of characters in it, and that's real graphemes in Perl 6. And we'll just loop over the lines, add it up. Okay. and close the file, say the characters. And I mentioned earlier that a loop calls pull1. So here's that pull1 method. So we call decoder consume line characters. Okay, we pass along whether we should chomp automatically, and then we have a fallback. So if it doesn't give us anything, we have to do a slow path get of the line, which might read from disk. And then if we still don't have anything, then we're at the end of the iteration, and we turn the iteration end sentinel. So just to show you some of the statistics that we get out of this, and if you run your program and you set the MVM special log, that is MoarVM specialization log environment variable to a file, you get all this information about your program. And here we can see this is the statistics for the chars method. Okay, it tells you where it's from, what line in the Perl 6 built-in source it's from. And you can see here that it got a lot of hits. And actually, every single time it was called with a concrete string. Okay, that is not the string type, but an actual string value. So that's kind of useful information. So here is the infix plus operator. Okay, again, a lot of hits, and all of the time it was called with a scalar container that we were allowed to assign into, containing an int, plus another int which wasn't in a container, so just a literal int, or an int value. So those, by the way, you're probably looking at and saying, these seem pretty hot, these seem pretty good candidates to optimize. This is why we need some data though. So here, this is read internal. This is the thing that actually goes off to disk, pulls some data in, and sticks it into the decode buffer. We've called it once. Okay, this is not, as of yet, worth spending any time optimizing, because it runs pretty rarely. We're not likely to get a good return on investment on this. Now, here's another interesting case. So this is the defined subroutine, and it got a lot of hits, so we'd call it hot. Okay, it's hot code, it's getting called a lot, but it's not getting called a lot on a scalar holding any. Okay, this isn't worth doing an optimization for. It's not getting called a lot on a string type object or an int, but it is getting loads and loads of calls on a string. Okay, so we know that these cases aren't worth producing an optimized version of the code for, but this one here is. For the loop body, okay, the loop body we can see always gets called with a string. So we didn't know what it was going to be. Now we can see it's very, very normally a string. And we also log a load of data inside of these methods as well. So for example, at this location, we can see we always call the static frame chars. We always get back an int from it, and we always pass it a string. Okay, so using that information, we can make a pretty good guess at exactly what method we're going to send it to and what sort of types it's going to have. So this can be kind of interesting data to sort of get a look at, because it's basically the optimizer's view of your program as it's running. So what do we do with this? Well, we have data, so it's time to make a plan. So we look at the total number of calls, and that tells us, okay, is this an interesting thing to spend time on? We look at how big the bytecode is, because the bigger it is, the more time we have to spend on it, and we sort of have a weighting based on that. And then we consider how morphic things are. And what I mean by morphic is it either monomorphic, polymorphic, or megamorphic? So monomorphic means we only ever see a single type show up. Okay, that's the mono. So this is pretty nice, because we're pretty sure that it's always going to be that. We allow a couple of outliers as well. Polymorphic is there's a few different types. Okay, and again, it's probably worth spending a bit of time on optimizing for each of those, because there's not many. Then we have megamorphic, and this is the case where, if we go and start trying to produce specialized versions of the code for every case, we're going to be in trouble, because we're just going to produce dozens of them and eat a lot of memory and time. So what we get out of this process is a plan. Okay, so this also shows up in that log file. And this says, okay, this is the specialization of plus, and we'll specialize it for the case where it gets that scalar container with an int plus an int. That's the one for mu.defined. Okay, you can see you got 98% of the call site hits, so we'll optimize it for that. It's sort of monomorphic-ish. It's close enough. Okay. Yeah, as I said, so for monomorphic and polymorphic, we try to make special versions of the code that deal with them. And for megamorphic, we just stick to simpler optimizations. Okay. Now, in the future, we'll actually try and do something in between. So we'll try and say, the first type is monomorphic, but the second argument is megamorphic, so we'll just optimize on one of them. And that shows up a lot in array accesses and hash accesses. So that's something for the future that we'll take a look at. Okay, so it's time to do some optimization. And let's take a look at how we might do that. So what we need is a representation of the program that is ideal for doing analysis and transformation. So the first thing we do is we take the instructions and we split them into basic blocks. And a basic block is a sequence of instructions that we are going to run through, and there's not going to be any flow control inside of it. So we're not going to go to some other place, we're not going to do a branch, okay? And in Perl 6, we have a lot of operations that we call invoke-ish, okay? They might invoke something, or they might not. So just to show you an example, this is the decontainerize instruction. This takes a value out of a scalar container. Now if it's a simple Perl 6 scalar, then that's just a very easy memory read. But if it's what we call a proxy, which you can think of, say in Perl 5 terms, like a bit like a tide scalar or something like that, then we have to call some code to do it. Type is the same. I told you type checking is pluggable. So this might call code, or in a good case, it might just quickly look in a little cache and give the answer. So we break it up into these blocks, okay? So they're all things that may invoke. And then we make a graph. And a graph is just a data structure with nodes and lines between them. And in this case, it's a directed graph because they have arrows. And that looks like that, okay? So you can see what's going on over here. This is a conditional. Okay, so this ends in an if statement or an unless or whatever. And we might go here, or we might go here. Okay, and then we join together again here. So this is an if, an else. And this jump back here, that's going to be some kind of loop. Okay, so we get a control flow graph like this. And we say that the things that you go to are your successors, and the things that you come from your predecessors, okay? So this basic block 5 has 2 predecessors, 3 and 4, and 2 successors, okay, 2 and 6. Now, control exceptions, we also try and represent in this graph. So, for example, the next handler, that's the redo handler, okay? Redo takes us to the top of the loop. So we actually put arrows on all of these, saying you could always maybe have a next handler, that, or a redo handler, sorry, that is taking you back to the top. The last handler could always take you out to the end. So you can see our graph gets a good bit more complex once we get exception handlers in there. For actual normal non-control exceptions, we don't yet do this. We actually link them all to the entry point. And that turns out to be safe for the analysis. It's a bit imprecise. So we will probably change that in the future. Now, a second important concept in this is that of dominance. Okay, don't laugh. Okay, okay, fine, do laugh. So basic block A dominates basic block B if every possible path from the entrance of the graph to that block goes through it. So if we think about basic block 1, to get to any of these other nodes, you have to go through 1. Okay, so we say that basic block 1 dominates all of those. Basic block 2, well, to get to all the rest of them, you have to go through 2. Okay, so it dominates all of those. A block dominates itself. Okay, so that's why those two just have themselves there. Basic block 5 here dominates basic block 6. The only way you can get to it is through 5. And basic block 6 is at the end. It doesn't dominate anything. Now, just to make this even more fun, we have a term called strict dominance, which just means excluding a block's dominance of itself. Okay, so those are the strict dominators. And we then have also the notion of immediate dominance. And immediate dominance is where a block strictly dominates something, but there isn't something else dominating it in the middle. Okay, so here, basic block 1 immediately dominates basic block 2, but if we think about basic block 3, okay, it's dominated by basic block 2, so it's not the immediate dominator. Okay, and if we just go through, okay, this immediately dominates all of these. Why doesn't 3 immediately dominate 5? Well, because you don't always go through 3 on the path to 5. Okay, so there we go. Okay, we get our immediate dominators. Now, if you're better at thinking about graph theory than I am, you might realize that these are unique. If we just take them, okay, and we actually plot them, they form a tree. Okay, so if we do that, okay, and then we can get rid of those, and if we just shuffle things around, it even actually looks like a tree now. And we call this the dominance tree. And successor and predecessor about control flow graph, parent and child are about the dominance tree. Okay, so these are node 2's dominance children, we would say. Now, why bother? Well, the first answer is the dominance tree is a really good order to visit code in when we want to optimize things. Okay, because we can propagate information in the order that things will happen. There's another reason though, and that is that we want to put the code into what we call single static assignment form. That is done by renaming variables. So what we have here is a bit of code. Okay, it takes 2 integer parameters. It then multiplies them. It multiplies the first one by itself, so squaring it. It adds the next parameter, and it returns it. And to turn this into single static assignment form, okay, we just rename each of these by just sticking a little index on it. So this is version 1 of this. This is version 1 of this. That's version 2. Okay. Now we have version 3 of R0. And the reason that we do this is that it makes it very easy for us to assign things we know about each of these and then know about that information later on in the analysis without getting really confused between the different versions of these variables. Now, what about control flow? Okay, because if I have, say, a maximum function, okay, so I rename these. This is all pretty easy so far. And here we have version 2 of this. But, okay, so we have version 2 of RO. We have version 1 of RO coming here. What should this be? Okay, and the answer is that we introduce what we call a phi function, which merges them, which looks like this. Okay, so we get another new version, which is the merge of these. And the other reason that we're really interested in dominance is because it tells us where to put those phis. Okay, through a slightly contorted method I'm not going to go into now. So SSA is really central to all of the optimizations that we're doing. Okay. Now, at the phi functions, we merge what we know. And there's another little bit of mathematics here called a lattice. And a lattice is basically something with a very simple rule: you always go up. Okay? You can always go up the thing. So for example, if I join an int and an int, okay, we can stay where we are. But if, for example, I see an int and a string, the only way to merge them is by going up, and that is what we don't know what type it is, because it's not a stable type. If we get an int and an unknown, the top type, okay, then again we have to go up there.
Just 5 minutes, please.
Okay.
Yep.
So, okay. So the final thing I want to throw in here is where do the facts come from? Okay. And sometimes we have static values, but sometimes they come from statistics. And then you might say, well, the problem with that is the statistics are only stats. They're not a proof. Okay, they don't prove that we always have a string at this point. They just say we normally have a string. So what we do is we insert a guard. And a guard is a very simple, very fast little check saying, is this what we expect? And that quick check is, if it's missed, going to have to do something. What is that something? And that is the answer to the question I posed at the start of the talk. How does deoptimization help us go faster? Deoptimization is what lets us do all of this statistical analysis, not worry about whether we can truly prove a property, quickly guard that we're meeting the property, and if the guard fails, we deoptimize. And what that means is we fall back to the interpreted code, which knows how to handle all of the cases. Okay? The consequence is that we must make sure we preserve enough data to be able to do that. We have to be able to fall back into the interpreter. So for example, in dead code elimination, occasionally we have to keep something that we would have liked to throw away. But we keep it so we can deoptimize. But in general, we win big. Okay, because the guards are very cheap. Something we would have checked in a lot of places, we lift up. And deoptimization is pretty rare because we built this statistical model to tell us about when it might and might not happen. Mix-ins are horrible because they change things at a distance. A mix-in actually causes what we call a global deoptimization. So what we do is we take the whole call stack and we throw away all the optimization and rewrite it all to interpret. Okay? So that gets back to the question. Now I was going to talk a little bit about some of the optimizations we do, but these are actually pretty standard things. What I do want to do though is just skip over this and show you the effect, okay, of these optimizations. This is the chars method. It's giant. Why is it giant? Because all of that is doing argument handling and type checks on the argument, checking that I don't expect you to read this by the way, checking that we actually got a string, we actually got a concrete string there. Here we actually do the work that we want to do. Okay, we take what are we doing there? Oh yes, we're getting the string out of its box. Okay, and we are getting the number of chars. We're boxing that into an int. All of that is a return type check. After optimization, using these guards, okay, it becomes that. That's a lot smaller. And you'll note it's a single basic block. Now there's still some crap in there that we want to throw away. Okay, we're not quite as smart as we'd like to be. But the amount of devirtualization we have done is quite incredible. This here, by the way, is actually just a very direct memory reference rather than doing an attribute lookup by name. That JIT compiles into just a couple of instructions, okay, to look up an attribute. So, all type checks removed, okay, and a few things that we'd like to get rid of when we're smarter in the future. Okay, so that basically brings me through the things I wanted to say. Let's just talk just very briefly about some of the things that I want to do in the future. So one of the things I'd really like to get us doing is avoiding boxing and unboxing things. This needs a bit more analysis going in there, but that's something that'll save a lot of memory allocation, a lot of work. One of the really big things I'd like to do is escape analysis. And what this does, you might have noticed Perl 6 allocates a lot of memory. But what we could do is we could try and analyze when that memory doesn't last longer than a particular method or subroutine call. And then we can actually say, well, let's just allocate it on the call stack rather than on the heap, and then we can throw it away much, much more cheaply. And that'll save us an awful lot of garbage collection overhead. I also want to make us more precise in this deoptimization handling. It's already pretty neat what we can do, but with a little bit more tracking of things, we'll be able to get rid of even more instructions and get things even cheaper. And I also want us to be a bit more aggressive. So when we do what we call inlining, where we take a subroutine we've called, or a method we've called, and just stick its code into the caller, so we completely get rid of the call, okay, then in that case, it would be nice if we could take the inline and then together with the thing it was put into, do optimization together on them, and we can maybe get some more out of that as well. So the other thing, finally, it would be nice if we had a bit more tooling on this, so that instead of getting a ginormous text file out, okay, you actually have a way to sort of ask about your code and see some information about what your code is getting some analysis done. And this is something that anyone who is interested in this area could work on. So I'll throw that out as a challenge for anyone who is sufficiently intrigued. Okay, so that's all. And okay, and I know I don't have time for questions, but I'll be around. So
just one. Would this be a point where coders could put hints to blocks or variables or whatever that the optimizer does not have to find out itself, but know it will never change or whatever?
Actually, part of the problem with that is that a lot of the things that we do basically violate memory safety, and you know we have to be really sure we can do them. So if the programmer tells us something and we just blindly believe it and we do an optimization based on it, the result could be segfault. Okay?
That's the problem of the programmer.
It could be, but it doesn't look good when the VM segfaults. Okay, so in the end, it turns out that we might have places we could try and do it as hints, but we'd still want to go and really put guards in and try to do some proofs. So, yeah. Okay, so thanks very much.